All right, hello everyone. Hi, welcome to the 8th short talk session. I'm really pleased to have 3 talks that we'll be presenting today. I'm going to start off with Hrach Asmerian, and he is at the University of California, Berkeley, and he's going to be giving us a talk about motor learning. So go right ahead, Hrach.
Cool. Share my screen. Can everybody see my screen?
Mm-hmm.
Cool. Can't really seem to see you guys though.
Oh, that's okay.
Cool. And you can hear me all right?
Yeah, if you could click on that hide button too, that would be useful.
Most definitely.
Perfect. Thanks.
Cool. So my name's Hrach, and today I'm going to be talking about motor learning and how we can identify some predictors of motor learning using a data-driven approach. So what's motor learning? Motor learning is anytime you use your motor abilities to learn something new and to adapt. So for instance, if you want to reach from some starting position to some target, you might fling your hand forward and notice that you've made some kind of error. Subsequently, you adjust to this error and so on and so forth until you complete your task and you adapt your motor system. And in the lab, this is typically studied using the apparatus you see on the left. So there's a desk setup where users are seated with a stylus in their hand and a digital display that hovers over the desk. And they can see where their stylus goes as identified by the white cursor on the screen. And in recent months and years, the Cognition and Action Lab at Berkeley has innovated methods, and now users can do this experiment online from the comfort of their home using an optical mouse or a trackpad. And this opens the door to many more users because this is so accessible, and also a greater diversity in people who take this kind of experiment. So much broader reach for this method. So typically, one example of motor learning task is the one shown on the right here. So initially shaded out in your hand is that you're reaching for some target, and your cursor is offset by some amount. There's some degree of rotation imposed on it. But eventually you adapt, you reach, in this case, to the right to get the cursor to the target. Well, this kind of adaptation is typically studied along some axis. So how does this adaptation vary with respect to, let's say, cerebellar ataxia, which we see on the left? So on the top 2 slides, you see the control subjects. It's a very standard adaptation curve once this rotation is imposed on their cursor versus their reach. But in cerebellar patients, we don't see that kind of adaptation and they plateau. And so this is one axis along which you can study adaptation. And another is task features instead of neurologic features. So Jonathan Say in the lab has worked extensively on this, working on what kinds of feedback on your screen influence how you adapt. So there's this whole space of features. And a big question is, how can we identify the important features for motor learning? And how can we let the data speak for itself instead of coming up with hypotheses and addressing them more individually? Well, first you need a task. So we developed a motor adaptation task. On the left, you're seeing average performance on these dots. And we recruited about 1,500 people. So this is a very, very substantial sample size in motor learning research. And on your screen, you'd see what's to the right here. So you move your cursor to the center and you reach for some target and you adapt. You get used to doing this task until you've gained some proficiency. And then we impose a rotation, just like I showed you earlier. Now, when you reach for the target, your cursor goes in a different direction and you have to figure out how to adapt. And that looks like what you see on the screen here. Your initial reaches are very far off until you figure out what's going on and put the pieces together. And on the left, you see the standard adaptation curve that correlates with this. And in the last phase, we instruct users to just reach back towards the target, but we don't give them feedback. So they can't adjust to errors. And we see residual effects from this adaptation rotation phase. So now that we have a motor adaptation experiment, we sought to see, is this a consistent metric of adaptation? So we compared the even and odd reaches of users over these different phases to see if they hold. So if your even and odd reaches on this task are not correlated whatsoever, then this can't hope to be a good metric of motor adaptation in the online world. But what we end up seeing is the opposite of that. Even and odd reaches along these different phases are very highly correlated, and this provides good within-user consistency. So this is a good metric. Also, we calculated Cronbach's alpha, which is another psychomotor consistency metric, and we got 0.92, which is fairly consistent. Also, Jonathan Say in the lab has worked extensively on this as well, showing consistency of online methods versus in-lab methods. So now that we have this performance in Reach, we look at the distribution. Along this early bracket, there's a fair distribution in performance between people. And same goes for late and after effect phases. So now we have a metric and we have differences with which to explore the feature space. And now we need features. So we collected roughly 20 demographic feature questions at the end of the experiment. And this revealed that there's a roughly equal split between optical and trackpad users. We recruited over 100 left-handed people, which is really novel in motor learning space. It's really exciting. And additionally, a greater diversity in racial groups of people who took this experiment, though still predominantly white and Asian, and an equal split between males and females. So in addition to these demographic features, we collected some task info in this baseline phase, like what were reaction times and movement times in the experiment. And we have all of these features, and we sought to predict one with the other. Using all of these demographic and task features we've accumulated in this space, how can we best predict motor adaptation outcomes? So we carried this out using a multiple regression method, namely LASSO Regression. And this method adjusts the weights within the model to best predict your outcome, and it shrinks some weights to zero. So it eliminates some variables from the feature space implicit in the method. So we use this method and cross-validate it to get the right hyperparameters so we have a good generalizable model. And we sought to predict early, late, and after effect phases of adaptation. So the result of these models is an explanation of variance between 2.4 and 11.8%. And what you see on the bottom left is 1,000 models generated on permutated data. So if I randomize demographic features and create models using this randomized set, how well can I predict actual outcomes? And it turns out, obviously it's very poor, and our predictions do much, much better than this baseline. Additionally, other studies in the same space of predicting a motor outcome using background information and task information capture variances in the same range. In this study in school-age children in motor adaptation, it's between 9 and 13. Though some other methods do get higher degrees of variance, I think it's important to note that these other metrics have vast batteries of motor ability, whereas we're studying the swipe of a finger or the movement of a mouse using background and task information. So I think given the task we're using, this is really substantial. So given that we have a model that can make these kinds of predictions, we can analyze the weights and see what does the best model use to figure out people's adaptation performance. And this is kind of a lot to take in. There's a lot of plots and a lot of different weights in early, late, and after effect phases, but I'm just going to zoom in on some of the ones I thought were important. So one are noted gender differences. So on the left, I've highlighted the features that fall under the group category of gender, how people reported it, and how that correlates with people's actual performance. And on the right, you see reach behavior separated by that metric. Though this is far from surprising given the history of motor learning research in this field, gender disparities have been found, and there's been a lot of work on gender stereotyping and training in the effects of this. And I think this provides credence to the model. This interfaces with the broader motor learning literature in a consistent way, at least in this way. But additionally, in addition to confirming some canonical findings, it offers areas for investigation we otherwise wouldn't have really looked into. So one of the most strongly positively weighed features was how people rated the experiment afterwards. So a 5 out of 5 rating would be satisfaction, great satisfaction with the experiment. 1 out of 5 would be poor. And we see a very close correlation with how well people did and how much they enjoyed the experience. And that wasn't really something we were thinking about testing beforehand or we thought was relevant. And the same goes for movement time. So how fast do you move your target from the starting position to the target? It turns out that the people who reacted faster had more accurate performance, pretty dramatically, if they were above the median, and vice versa for longer movement times. So these provide some new areas for investigation where you wouldn't really anticipate differences. And additionally, features that are removed are also really important. So one would expect that there would be some difference between mouse and trackpad performance because it seems to be a different movement. One is with a finger and one is more gross motor activity. But the fact that there isn't much difference along this axis says that this is a pretty consistent method. This is a reliable way to study this motor adaptation. Additionally, major didn't really seem to interface with differences in adaptation, which was also interesting. And very quickly, in this after effect block, as you see on the right with the black bracket over it, the greatest differences were dramatically found on the direction of the target. And this was a very unexpected finding, and we weren't really thinking about this direction at all, but this shined a light on this influence. So roughly, whether or not your target fell in diagonal directions or cardinal ones, which is north, south, east, and west, made a huge difference in this residual implicit component of motor adaptation, thus shining a light on something important we otherwise wouldn't have really come across. So just to wrap up, this method of regression and selecting features within it shines a light in the dark space of all of the features. And sure, we can't capture all of the features out there, but this is a big step from an individual hypothesis test. And additionally, it's data-driven. The data speaks for itself. You don't need to have all of these priors and one very explicit question coming into it. You let the model paint the picture of what seems to be important. Also, it reveals novel features you would have never anticipated being important that can eventually paint directions for future research. And yeah, I think this is really exciting work. And I want to thank Jonathan and Rich from the Cognition and Action Lab, as they've helped my thinking along this line. And also Laura, Jeremy, and Ken from testmybrain.org, which is where this experiment was initially offered. Also, if anybody's interested, you could take this experiment. It's online right now. If you follow this link, multiclamp c2 web.app. And I also want to thank Neuromatch because I think this is such a great opportunity for people to see the work that's out there and get constructive feedback. And yeah, I just want to say thanks a lot for the opportunity.
Wow, that is really fascinating. I can't believe that you can get such great data out of an online forum like this. That's great.
Seems like I'm getting a feedback loop here.
Uh-oh.
Whoa. Do I not share? This is strange. Oh, there we go. I'm back. Sorry about that. Oh, I think you're muted.
So that was great. That was really fascinating. One of the questions that I immediately had in thinking about the fact that you can do trackpad versus mouse is whether there are residual after effects if you train them up on trackpad and then have them switch to mouse.
Yeah, that would be.
Have you tried that one yet?
No. So in this experiment, people just log on and report what they used. So we don't really designate what people should or shouldn't use. On the website, it says recommended trackpad because that was our initial line of inquiry, but it ended up being 50-50.
Right.
But I do remember reading a paper, I forget from when, but there was a disparity between different ages and using a mouse versus a trackpad. And I didn't see these effects clearly laid out in my data, but also great line of inquiry. Like, because they are different motions, this calls into question, like, is it really the same underlying system that we're calling upon? And I wonder if switching between methods would illuminate this.
Well, yeah, absolutely. Do you mind also saying, talking about what software stack you used for this? Was this,
I use RStudio and a fair set of the machine learning packages like GlimNet and all of those.
Oh, no, sorry. I meant for actually running the experiments and collecting the data online. Was that
Oh,
JavaScript?
it's called OnPoint. I believe it's coded in Java, and it was developed by some graduate students in my lab.
Okay, great. Yeah. Is that something that's available for other people to use?
Yeah, open access.
Great. Fantastic.
Yeah, great tool. Really, sample size is the big contributing factor here. In motor learning research, how are you going to recruit 1,500 people
Sure,
to
right.
come into your lab and move a stylus? So I think this paints the way for larger big data approaches to these problems.
Absolutely. We got just a little bit of time for questions since we started late. John Patterson asks if you looked at the history of gaming.
Yeah, one of the questions we asked was how many hours a day do you play video games? And we mapped that as a continuous feature. That was one of the weight features in the model, positively predicting. So more hours of video game playing is a positive predictor of adaptation. Although I think it's important to know, I didn't have time to really dive into this, but a limitation of multiple regression is that if you have two features that explain the variation identically, no model is going to tell you which one is the real proximate cause of it. And I think this is underlying deeper problems and what we mean when we say, oh, there's a close correlation between these features. So for example, I had this problem with age and education. They were very, very closely correlated as the correlation matrix revealed. And this poses a problem. So for example, education was included in my model, but age was dropped. And does that really make sense? It's a shortcoming of multiple regression. So if you use other tools like a correlation matrix to highlight these questions, which I'll do in the discussion, you get around this problem.
All right. Well, in the interest of time, I think we're going to move on. Sorry, Franz, if you want to ask that question, you could maybe bring it up in the Discord channel associated with this talk. By the way, the Discord server is not going away at the end of the conference, so please feel free to continue to have conversations there as we move on. So Hrach, thank you very much. That was a great. I just love the idea that you can collect data in this format and then it has such validity. That was great.
Yeah, thanks so much.